Hello and welcome to Earth Science, Lecture 22, Air Masses, Fronts, and Midlatitude Cyclones. For many people who live in the middle latitudes, which includes much of the United States, summer heat waves and winter cold spells are familiar experiences. In the first instance, several days of high temperatures and oppressive humidity may finally end when a series of thunderstorms passes through the area, followed by a few days of relative cool relief. By contrast, the clear skies that often accompany a span of frigid sub-zero days may be replaced by a thick, gray cloud and a period of snow as temperatures rise to levels that seem mild compared to those just experienced days earlier. In both examples, what was experienced was a period of generally constant weather conditions, followed by a relatively short period of change, and then the re-establishment of a new set of weather conditions that remained for some time before changing yet again. The weather patterns just described result from movements of large bodies of air known as air masses. An air mass, as the term implies, is an immense body of air, usually 1,600 kilometers or 1,000 miles or more across, and perhaps several kilometers thick. This is characterized by a similarity of temperature and moisture across a given given altitude. When this air moves out of the region of origin, it will carry these temperatures and moisture conditions with it, eventually affecting a large portion of some continent. An excellent example of the influence of an air mass, as illustrated in the figure, shows a cold, dry air mass from northern Canada moving southward. With a beginning temperature of about negative 51 degrees Fahrenheit, the air mass warms to negative 27 degrees Fahrenheit by the time it reaches Winnipeg. It continues to move and warm as it moves southward through the Great Plains and into Mexico. Throughout the southward journey, the air mass becomes warmer, but it also brings some of the coldest weather of the winter to places in its path. Thus, the air mass is modified, but it also modifies the weather in the area over which it passes. The horizontal uniformity of an air mass is not perfect, of course. Because air masses extend over large areas, small differences occur in temperature and humidity from place to place. Still, the differences observed within an air mass are small compared to the rapid changes experienced across air mass boundaries. Since it may take several days for an air mass to move across an area and be modified, the region under its influence will likely experience fairly constant weather, a situation known as air mass weather. Certainly there are some day-to-day variations, but the weather will be relatively consistent until an air mass boundary comes through and a different air mass influences the area. The air mass concept is an important one because it closely relates the study of atmospheric disturbances. Most disturbances in the middle latitudes originate along boundary zones that separate different air masses, which we'll get into very soon, known as fronts. When a portion of the lower atmosphere moves slowly or stagnates over a relatively uniform surface, the air assumes the distinguished feature of that area, particularly with regard to temperature and moisture content. The area where an air mass acquires its characteristics of temperature and moisture is called the source region. Air masses are classified according to their source regions. So we break them down in two different ways, as you can see on this slide. We first break them down as either polar, Arctic, or tropic. Polar air masses, or P air masses, and Arctic, or A air masses, originate in the high latitudes toward the Earth's poles, whereas those that form in low latitudes are called tropical, or T air masses. The designation polar, Arctic, or tropical gives an indication of the temperature characteristics of the air mass. Polar and Arctic indicate cold, while tropical indicates warm. In addition, air masses are classified according to the nature of the surface of that source region. There is either continental or sea air masses that form over land, or maritime M air masses that originate over water. The designation continental or maritime thus suggests the moisture content of the air mass. Continental air is likely to be dry, while maritime air is likely to be humid. So we have multiple types of air masses. The basic types of air masses, according to this scheme of classifications, are continental polar, or CP, continental Arctic, or CA, continental tropic, CT, or we have the maritime ones, maritime polar, MP, or maritime tropical, MT. So we have this wide variety of different air masses, whether they originate over land or water, and whether or not they're Arctic, polar, or tropical. Source regions are largely confined to the subtropical and subpolar locations. The fact that the middle latitudes are where cold and warm air masses clash, often because the converging winds of the traveling cyclone draw them together, means that this zone lacks the conditions necessary to be a source region. So notice the United States in these images isn't a region of source. The other air masses just happen to move into this area. The differences between polar and Arctic are relatively small and serve to indicate the degree of coldness respective to the air masses. So let's discuss air mass weather. Continental polar and maritime tropical air masses influence the weather of North America the most, especially east of the Rocky Mountains. Continental polar air masses originate in northern Canada, interior Alaska, and the Arctic, areas that are uniformly cold and dry in the winter and cool and dry in the summer. In winter, an invasion of continental polar air brings the clear skies and cold temperatures that we associate with a cold wave as it moves southward from Canada into the US. In the summer, this air mass may bring a few days of cooling relief. Although CP air masses are not, as a rule, associated with heavy precipitation, those that cross over the Great Lakes during late autumn and winter sometimes bring snow to the leeward shores. These localized storms often form when the surface weather map indicates no apparent cause for a snowstorm. These are known as lake effect snows, and they may make Buffalo and Rochester, New York, for example, among the snowiest cities in the United States. So what actually causes lake effect snow if there's no necessarily storm passing over? During late autumn and early winter, the temperature contrast between the lakes and the adjacent land areas can be large. The temperature contrast can be especially great when a very cold CP air mass pushes southward across the lakes that is not yet frozen over. As this cold, free air moves across, say, Lake Superior, clouds develop because the air acquires a large quantity of heat and moisture from the relatively warm lake below. By the time the CP air reaches the opposite shore, the air mass is more humid and unstable, and so heavy snow showers can occur. Maritime tropical air masses affecting North America most often originate over the warm waters of the Gulf of Mexico, the Caribbean Sea, and the adjacent Atlantic Ocean. As you might expect, these air masses are warm, moisture-laden, and usually unstable. Maritime or MT tropical air is the source of much, if not most, of the precipitation in the eastern two-thirds of the United States. In summer, when an MT air mass invades the central and eastern United States, and occasionally southern Canada, it brings the higher temperatures and impressive humidity typically associated with its source region. During the winter, maritime polar air masses coming from the North Pacific Ocean often originate as continental polar masses in Siberia. The cold, dry CP air is transformed into relatively mild and humid, unstable MP air during its long journey across the North Pacific. As this MP air arrives at the western shore of North America, it is often accompanied by low clouds and shower activity. When this air advances inland against the western mountains, orographic uplifting produces heavy rain or snow on the windward slopes of the mountain. Maritime polar air also originates in the North Atlantic off the coast of eastern Canada, and occasionally influences the weather on the northeast side of the United States. In winter, when New England is on the northern or northeast side of a passing low-pressure system, the counterclockwise cyclonic winds draw in maritime polar air. The result is a storm characterized by snow and cold temperatures known locally as a nor'easter. So you can see an example of a nor'easter here. So here's the northeast United States, and here's our low pressure system moving through, giving us the nor'easter that we typically find in the winter. One prominent feature of mid-latitude weather is how suddenly and dramatically it can change. Most of these sudden changes are associated with the passage of weather fronts. Fronts are boundary surfaces that separate air masses of different densities, one of which is usually warmer and contains more moisture than the other. However, fronts can form between any two contrasting air masses. When the vast sizes of air masses are considered, the zones or fronts that separate them are relatively narrow and are shown as lines on a weather map. Generally, the air mass is located on one side of the front moves faster than the air mass on the other side. Thus, one air mass actively advances into the region occupied by another and collides with it. During World War I, Norwegian meteorologists visualized these zones of air mass interactions as analogous to battle lines and tagged them fronts, as in battle fronts. It is along these zones of conflict that storms develop and produce much of the precipitation and severe weather in the belts of the westerlies that we have here in the United States. As one air mass moves into a region occupied by another, minimal mixing occurs among the front surfaces. Instead, the air masses retain their identity as one is displaced upward over the other. No matter which air mass is advancing, it is always the warmer, less dense air that is forced aloft, whereas the cooler, denser air acts as a wedge on which the lifting occurs. The process of warm air gliding up and over cold air masses is termed overrunning. So let's take a look at each type of front. When the surface position of a front moves such that warm air occupies territory formerly covered by cooler air, it's called a warm front. On a weather map, the surface position of a warm front is shown by a red line with red semicircles protruding into the cooler air. The direction of the symbols are pointing in the direction the front is moving. East of the Rockies, warm tropical air often enters the United States from the Gulf of Mexico and overruns receding cool air. As the cool air retreats, friction with the ground slows the advance of the surface position of the front more than it does aloft. Stated another way, less dense warm air has a hard time displacing the denser colder air. For this reason, the boundary separating these air masses acquires a very gradual slope. So in other words, there's a lot of friction at the surface, so the front moves more slowly at the surface than it does up high where there's no friction. So the front actually is angled upward at a very shallow angle. The average slope of a warm front is a ratio of about 1 to 200, which means that if you are 200 kilometers ahead of the surface location of the warm front, you will find that the frontal surface is at a height of about 1 kilometer. So in other words, that's saying if this is 200 kilometers from the start of the front to, say, Pittsburgh, then this is 1 kilometer. Not to scale, of course. So what would you experience in terms of weather in such a scenario? Well, as warm air ascends the retreating wedge of cold air, it expands and cools adiabatically, as we learned previously, so it will produce clouds and frequently precipitation. The sequence of clouds shown in this figure typically precedes a warm front. The first sign of an approach of a warm front is the appearance of cirrus clouds overhead. So note, here is the front way over here, but ahead of the front we get all this precipitation. So the very first thing that we typically see is the high cirrus clouds, those wispy layers with the little curves in the ends. So as the front nears, cirrus clouds grade into cirrostratus clouds, which blend into denser sheets of altostratus clouds. About 300 kilometers, or 180 miles ahead of the front, thicker stratus and nimbostratus clouds begin to appear, and rain or snow may begin. Because of their slow rate of advance and very low slope, Warm fronts usually produce light to moderate precipitation over a large area for an extended period of time. This precipitation is often in the form of snow in the winter. During late fall and early spring, the precipitation often changes from snow to sleet to freezing rain, and finally to rain as the warm front approaches. Warm fronts are occasionally associated with thunderstorms in the spring and fall. This occurs when the overrunning air is unstable and the temperatures on opposite sides of the front contrast sharply. At the other extreme, a warm front associated with a dry air mass could pass without creating clouds or precipitation. A gradual increase in temperature occurs with the passage of such a front. The increase is most noticeable when there is a large temperature difference between the two adjacent air masses. The moisture content and stability of the encroaching warm air mass largely determined when clear skies will return. During summer, cumulus and occasionally cumulonimbus clouds may be embedded within the warm, unstable air mass that follows the front. Precipitation from these clouds can be heavy, but is usually scattered or of short duration. When dense cold air is actively advancing into a region occupied by warm air, so the opposite of what we've been discussing thus far, the boundary is called a cold front. As with warm fronts, friction tends to slow down the surface position of the cold front more than it does aloft. However, because of the relative positions of the two adjacent air masses, the cold front steepens as it moves. So instead, if we go back, instead of it moving this way and the ground slows the bottom down so the front is moving ahead of it, well, now we have the cold air moving in front. So the wedge is kind of backwards now, but it's still moving from left to right. So in this case, the front edge of this is actually bent downward because it's slowed down at the surface. So as a result, we actually get a much steeper incline for our cold fronts. And this is important. On average, cold fronts are about twice as steep as warm fronts, having a slope of perhaps 1 to 100. In addition, cold fronts advance at speeds of around 20 to 35 miles per hour, compared to 15 to 20 miles per hour for warm fronts. These two differences, the rate of movement and the steepness of the slope, largely account for the more violent nature of cold front weather compared to the weather generally accompanying a warm front. As a cold front approaches, commonly from the west or northwest, towering clouds can often be seen in the distance. Near the front, a dark band of ominous clouds foretells the coming weather. The forceful lifting of air along a cold front is often so rapid that the latent heat released when water vapor condenses appreciably increases the air's buoyancy. The heavy downpours and vigorous wind gusts associated with mature cumulonimbus clouds frequently result. So in other words, the air here is basically just forced to rise faster, and as a result, we see our clouds build up and give us more thunderstorms and heavy precipitation instead. A cold front produces roughly the same amount of lifting as a warm front, but over a shorter distance. As a result, the intensity of precipitation is greater, but the duration is often shorter. In addition, a marked temperature drop and a wind shift from the south to west or northwest accompanies the passage of the front. The sometimes violent weather and sharp temperature contrast along the cold front are symbolized on a weather map by a blue line with blue triangle-shaped points that extend into the warmer air mass. The weather behind a cold front is dominated by a subsiding and relatively cold air mass. Thus, clearing usually begins soon after the front passes. Although the compression of air due to the subsidence causes some adiabatic heating, the effect on the surface temperature is minor. In winter, the long, cloudless nights that often follow the passage of a cold front allow for the abundant radiation cooling to reduce the surface temperatures. When a cold front moves over a relatively warm area, surface heating can produce shallow convection. This in turn may generate low cumulus or stratocumulus clouds behind the front. But warm and cold fronts are not the only types of fronts. There's actually two others we'll focus on. Occasionally, the flow on both sides of a front is neither toward the cold air mass nor toward the warm air mass, but almost parallel to the line of the front. Thus, the surface position of the front does not move. This condition is called a stationary front. On a weather map, stationary fronts are shown with blue triangles pointing toward the warmer air and red semicircles pointing toward the cooler air. At times, some overrunning occurs along a stationary front, causing gentle to moderate precipitation. Flooding can occur along the cold side of a stationary front if the front remains in place for a long time. The fourth type of front is an occluded front, an active cold front that overtakes a warm front. As the advancing cold air wedges the warm air upward, a new front emerges between the advancing cold air and the cool air. The weather on or near a occluded front is generally fairly complex. Most precipitation is associated with the warm air being forced aloft. When conditions are suitable, however, the newly formed front is capable of initiating precipitation of its own. Occluded fronts may result in heavy rain in the warmer months or a blizzard in the winter. On a weather map, occluded fronts are shown with purple triangles and semicircles, both pointing in the direction of the front's advance. So note, because it's a cold front catching up to a warm front, we combine the blue and red colors to give us purple, and so we combine the triangle and semicircle shapes. And again, the precipitation here is typically formed because the warm air is being forced upward. You basically have two wedges of cold or cool air coming together, so the warm air is forced to move up. So we can kind of combine all of these now and discuss mid-latitude cyclones. So far, we have examined the basic elements of weather, as well as the dynamics of atmospheric motions. We are now ready to apply our knowledge of these diverse phenomena to an understanding of day-to-day weather patterns in the middle latitudes. For our purposes, middle latitudes refers to the region between southern Florida and Alaska. The primary weather producers here are mid-latitude cyclones. On weather maps, they are shown by an L, meaning low pressure system. Mid-latitude cyclones are large centers of low pressure that generally travel from west to east. Lasting for a few days to more than a week, these weather systems have a counterclockwise circulation with an airflow inward toward their centers, as we learned about in our previous lecture. Most mid-latitude cyclones also have a cold front extending from the central area of low pressure, and frequently a warm front out front as well. Convergence and forceful lifting initiate cloud development and often cause abundant precipitation in the vicinity of the low-pressure system. As early as the 1800s, it was known that mid-latitude cyclones were the bearers of precipitation and severe weather. But it was not until the early part of the 1900s that a model was developed to explain how cyclones form. A group of Norwegian scientists formulated and published this model, created primarily from near-surface observations made in 1918. Years later, as data from the middle and upper troposphere and from satellite imagery became available, modifications were necessary. However, this model is still a useful working tool for interpreting the weather. If you keep this model in mind when you observe changes in the weather, the changes will no longer come as a surprise. You should actually begin to see some order in what once appeared to be disorder, and you might even occasionally be able to, quote, predict the impending weather. So let's take a look at how we can do this. We're going to step through mid-latitude cyclone weather from the points A through E. So just imagine this is sitting stationary, this storm system, and we're just going to take a journey from A to B to C to D to E. So just imagine we're cutting through there. And here's a side view of this area. So from A to E, here's A to E. So refer to this image as I step through. Using the figure as a guide, we can consider the weather producers and what we should expect from them as we move over an area. So imagine the change in weather as you move from A to E. At point A, the sighting of high cirrus clouds would be the first sign of an approaching cyclone. These high clouds can precede the surface front by 600 miles or more, and they are generally accompanied by falling pressure. As the warm front advances, a lowering and thickening of the cloud deck is noticed. Usually within 12 to 24 hours after the first sighting of cirrus clouds, light precipitation will begin, as it does at point B. As the front nears, the rate of precipitation increases. A rise in temperature is noticed, and winds will begin to change from east or southeast to south or southwest. So you can see this here. Winds are coming in from the east or southeast, and now they're going to change to be coming in from the west or southwest. With the passage of the warm front, the area is under the influence of maritime tropical air, such as at point C. Generally, the region affected by this sector of the cyclone experiences warm to hot temperatures, southwesterly winds, fairly high humidity, and skies that may be clear or contain cumulus clouds. The relatively warm, humid weather of the warm sector passes relatively quickly and is replaced by gusty winds and precipitation generally associated along the cold front. The approach of a rapidly advancing cold front is marked by a wall of dark clouds as in point D. Severe weather accompanies this heavy precipitation with hail and occasional tornadoes in it, with a definite possibility, especially during the spring and summer months. The passage of the cold front is easily detected by a wind shift from the southwest winds that we were experiencing to a more westerly or northwesterly wind, as pronounced by a drop in temperature. Also, the rising pressure hints that the subsiding cool, dry air is behind the front. So last but not least, we're on the other side of the cold front now at point E. Once the front passes, skies will begin to clear as cooler air invades the region. Often a day or two of almost cloudless deep blue skies occurs unless another cyclone is edging into the region. Well, you'll notice that there's also two other points labeled on this graph, F to G, so we're going to take a journey through that as well. So here we have again a picture of that same mid-latitude cyclone and a cutout from the side, but this time up north from F to G. So as you can probably look at in the images, a very different set of weather conditions prevails in the regions north of the storm center along the profile from F to G. Temperatures progress from cool at F to cold at G. The first hints of approaching low pressure are the decreasing air pressure and increasingly overcast conditions that begin varying amounts of precipitation. This section of the cyclone most often generates snow during the winter months and heavy rain during the warmer months. Once the formation of an occluded front begins, which you can see actually right at the top here, the purple one where the cold front overtakes the warm front, the character of the storm begins to change. Because occluded fronts tend to move more slowly than the other fronts, the entire wishbone shape structure of the storm begins to rotate counterclockwise. As a result, the occluded front appears to bend over backwards. This effect adds to the misery of the region influenced by the occluded front because it lingers over an area for longer than it would otherwise. And so you get this comma head shape as it begins to turn over itself, and as a result, you have continued cloud cover longer than you would have had previously. So please pause the video and watch the cyclone animation in the YouTube description or at the following link. So remember, we learned about in our last video that this is a low pressure system, which means air is converging at the surface. Well, if it's doing that, it has to go somewhere, which means it has to go up. So when the earliest studies of mid-latitude cyclones were made, little was known about how the nature of the airflow in the middle and upper troposphere worked. Since then, a close relationship has been established between surface disturbances and the flow aloft. Airflow aloft plays an important role in maintaining cyclonic and even anticyclonic circulation. In fact, more often than not, these rotating surface winds are actually generated by the upper level flow. Recall that airflow around a surface cyclone or a low pressure system is inward, a fact that leads to convergence of the coming air. The resulting accumulation of air must be accompanied by a corresponding increase in pressure. Correspondingly, or consequently, we might expect a low pressure system to fill in the rapid area. However, this does not occur. On the contrary, cyclones often exist for a week or longer. For this to happen, surface convergence must be offset by a mass outflow of some level aloft. As long as divergence or spreading out aloft is equal to or greater than the surface inflow, the low pressure is accompanying convergence can be sustained. So I think I slaughtered some of the words there, but the idea is as air converges inward here, it has to go somewhere. But for it to be maintained and for this to keep going on, it has to diverge at the top. So wind swirls in at the top and then gets kind of spit out and ejected at the top. And the opposite is true for high pressures or anticyclones. Because cyclones are bearers of stormy weather, they have received far more attention than anticyclones. Anticyclones, or high-pressure areas on a weather map, represent the air masses that were discussed earlier. For example, the surface high pressure shown in the image is likely a continental polar air mass. Because a close relationship exists between surface highs and lows, it is difficult to separate any discussion of these two types of pressure systems. The surface air that feeds a cyclone, for example, generally originates as air flowing out of an anticyclone. Consequently, cyclones and anticyclones are typically found adjacent to one another. Like a cyclone, an anticyclone depends on the flow far above to maintain its circulation. Divergence at the surface that you see here, air flowing away from the high pressure, is balanced by convergence aloft and generates the subsidence of the air column. So air sinks, again, as we learned at high pressure systems, which is why we don't typically see a lot of stormy weather with them. It spreads out at the surface, converges at the low pressure surface area, and then rises again. So I wanted to show you a really interesting example. So I'm filming this right now. It's March 18th of 2019. Several days ago, the United States experienced one of the strongest low pressure systems ever recorded over the central United States. So here's a surface map from March 13th, just 5 days ago. And I mean, for those that are watching this relatively soon after I record it, this will probably make sense. You'll probably remember this storm. Of course, if you're watching this years from the recording, then maybe not. But the point is, a storm developed over the central United States. It underwent something called bombogenesis, which just means that its pressure drops significantly in a short amount of time. So what you can see here, it's a little more complex than the more simplified versions we've been looking at. But here is the center of that low pressure system, the big L right here. You can see the occluded front in purple, the cold front, and the warm front, just like we saw here. We see the occluded front near the low, a cold front, and a warm front. So here it is again. Now, notice a couple different things. First of all, the isobars are close together near the low pressure system. So if you watched the previous lecture, you'll know that the closer the spacing is, the stronger the winds are. And the further away the spacing is, like way out here on the Atlantic coast, the lower the winds should be. So what I'm going to show you in the background is an actual profile of the wind at the time of this surface map, or very close. And you can actually pick out some of these fronts. And notice, again, that the winds are strongest near the low. So let's take a look. So here is the surface map of winds at the time of this low pressure system. Notice so many things are important here, and I really love to show this off. First of all, you can tell where the center of the low pressure system is, and I'll keep playing this. You can see, second, that the winds swirl in a counterclockwise direction for this low pressure system, and they're converging. You can see all the wind is funneling into this area. So everything we just learned about low pressure systems is kind of confirmed by this map. Now also, you can tell that the winds are moving fastest here and quite slow out in the Atlantic, just like we described. Also, you can sort of pick out where the cold and warm fronts are. We're just going to focus on the main two here, but here's the cold front cutting through close to the Texas coast. Okay, so kind of close to where we are in Durant, or at least where I am. So take a look at the cold front here, and now let's return to the map. Well, look at that. You can actually see the cutout of this cold front right there. And if you look, We have a warm front not far away from that over Louisiana and cutting into the Gulf of Mexico. And here it is, right along here. You can see it curving backward. So you can actually kind of picture everything that we discussed in this single wind map. And I think that's incredible. Now also, if we take a look up here, we can kind of see some winds diverging a little bit. So there's probably some high pressure systems up here in this area. And sure enough, there it is, right off the coast. So this is really incredible, I think, to compare something that looks fairly complicated in this surface map and then just put it to a map of the winds and actually be able to pick these things out. So I hope you learned quite a bit with this discussion. We're going to go through, let's say, 2 quick questions to close out this lecture before we move on to my favorite lecture, which is on severe weather. As a storm chaser, of course, I'm going to kind of nerd out with that one. So let's go through 2 questions. Number 1, say you live in the Midwestern United States or Canada, and you experience several days of winter temperatures below 20 degrees Celsius with clear weather. What are you likely experiencing? Okay. In this case, because it's so cold and you have constant clear weather, it's a continental polar air mass. These are the air masses that bring cold weather and clear weather with them for quite some period of time. Number 2, typically cold fronts blank. All right, in this case, because the cold fronts are advancing with a very steep angle and they move faster, the air is rising more violently in the region around a cold front, and as a result, it brings about more violent weather than the warm fronts do. All right, so as always, thanks for watching and have a great day.